When we create something, we often leave traces of our internal decisions. I like finding patterns in mine and formalizing them into rule sets. This way I can translate my creative intuition into algorithms and have the computer amplify my process and co-create with me. But this takes time and expertise, rendering it inaccessible to many. I don't think it should be that way. I believe we can minimize the gap between expressing creative intent and realizing it. And I believe we can do it with algorithms that learn from the user's examples, enabling more people to amplify their work with personal tools, which they create by simply expressing themselves in their creative media. And today we will have a look at an instance of such an algorithm that infers rules from a user example of object placements. Welcome to Place Like I Do, example-based procedural placements in a dialog system. My name is Anastasia Opara, and I'm a procedural artist at Embark Studios. So you might be wondering, what is example-based procedural placement? When creating a scene, probably the most common way of doing it would be placing each asset by hand. However, that quickly becomes tedious, especially for larger scenes, and any future modification will have to be carried out by hand too. Thus, the creative iteration loop of how fast we can explore new ideas and iterate on existing ones becomes stifled by execution time it takes for each iteration. Another way would be to write a small procedural algorithm to have the computer do the tedious work for us. However, writing an algorithm requires translating creative intent into a logic-based code, which is time-consuming and poses a knowledge barrier for many. And it also forces us to interrupt our creative loop to solve the idea-to-code translation problem. With example-based placement, we would like to automate this process, thus reinforcing our creative loop without interrupting it. And we do so by asking the user to provide an example of what they want, which we automatically analyze and break down into rules. And with these rules, we can synthesize new, similar-looking content. And there are many ways how one can design an interaction with example-based placement algorithm. So I'd like to give you a peek into one of our latest experiments, where we used example-based placement as a vehicle to explore a feeling of co-creation with a procedural system in a dialogue-like interaction. In our experiment, we embodied the example-based procedural placement algorithm into this little creature, whom we named Kittus. Kittus tries to assist you by mimicking your placements. It analyzes the neighborhood of objects you place and finds similar-looking locations in the level. So if you place grass near a tree and a rock, Kittus will place a new grass near another tree and a rock, using your previous placement as an example. And by going back and forth between you and Kittus, you end up co-creating a small scene together. And sometimes Kittus cannot find a perfect match to your placement, but that's when it becomes interesting, as it has to improvise. And this I place, you place interaction was a part of slightly bigger experience, a project called Kittiwake, where you are on a small planet and together with multiple kitty, you populate it with assets and give it a bit of life. This is how Kittiwake looks like. This is a recording of me playing a session. In this demo, we had a slightly different interaction to the previous test you've seen. Here you have to copy an existing object to place a new one. And by positioning objects in specific patterns, you unlock new objects, sort of progressive asset discovery. And some objects interact with each other if located nearby, to introduce a second-order effect to your and Kitty placements. Overall, Kittiwake was a very educational experience for us. We released it internally on our own tech stack written in Rust. We got a bunch of awesome user feedback. For example, embodying the algorithm into a personified creature established an emotional connection, and it was a lot of fun observing people play with Kitty, surfacing such questions as, what is the ideal relationship with Kitty? Are they just your tools, like your slaves obeying blindly, or more like pets that can have a mischievous mind of their own? At the same time, Kittiwake evoked a more micromanagemental mood than we intended, due to Kitty and user sharing the same action space of direct placements. One can probably do a separate, purely UX dedicated talk about Kittiwake, but this presentation is more about how Kitty work on the inside. So we're going to talk about a lot of fairly technical things that comprise the Kitty brain, such as concept of possibility space, sampling that space with Markov chain Monte Carlo, defining similarity metric for spatial arrangements of objects, and also have a brief introduction to optimal transport and WASSERSTEIN distance. If those are the things you've never heard about, don't panic. My main goal is to give you an intuition about these algorithms and hopefully inspire you to use some of them in your own work. So let's start our deep dive by introducing you to Kittus Bob and Kittus Mary, whose placements we will use as an example. Bob and Mary like being close to each other. but not too close. They do like their personal space. And being too far apart is also not great and makes them sad. One can say they have a very functional relationship, meaning we can express Mary's and Bob's happiness as a function of their proximity to one another. The relationship can be captured with a graph like this one, where the bottom axis is a distance between Bob and Mary, and the upper axis is how happy they are with each of those placements. Now suppose Bob and Mary are moving into a new town. It's a lovely, one-dimensional street with an exquisite selection of one-dimensional locations to choose from. And we are faced with the task of finding a new home for Bob and Mary that would make them happy according to their happiness function, which says that they are most happy when they are about 1 meter apart. But instead of reasoning about Bob and Mary in world space, let's separate Mary's and Bob's location into their own axis. Thus, any configuration of Bob and Mary can now be expressed as a point in this new two-dimensional space. For example, this point with the coordinate 4 and 6 simply represents that Mary is on coordinate 4 and Bob on coordinate 6. And now we can very easily explore all possible Bob-Mary placements just by moving around in this new two-dimensional space, which we will call possibility space, since it describes all possible Bob-Mary configurations. Note how every configuration corresponds to a certain value in the score function, indicated by the moving yellow dot. We can evaluate that score for every point in the possibility space and visually see where good Bob-Mary configurations tend to form. In general, we are interested in the regions of high scores, indicated by yellow dots in the possibility space. And as you can see, there are a lot of good solutions, and we can pick any of them to generate the final placement that would make Bob and Mary happy. We can also change the initial score function and see how regions of good solutions change as well. For example, if we introduce bimodality to our score function, making Bob and Mary either wanting to be super close or 5 meters away from each other, that is also reflected in our possibility space, as well as in the final solutions we present in the world. One can say that the regions of good solutions are shaped by Mary's and Bob's score function, which I find conceptually very interesting if you think of this function as a sort of soft rule or condition that we are trying to meet. And possibility space represents all possible outputs of our algorithm, meaning that the rules are not defined explicitly in code, but rather are parameters of our algorithm. In turn, that means that with the same piece of code, we can generate all kinds of Bob and Mary placement configurations just by changing the score function. But so far, we've only talked about 2Kitty, meaning our possibility space was defined by only 2 parameters, making it two-dimensional and easy to visualize and talk about. But suppose Mary's distant cousin decides to also move in. Well, now when reasoning about good solutions, we need to take his position into account too, making our possibility space 3-dimensional. Now imagine the whole family decides to move in, and they all have special requests, such as someone wants to live close to Mandy, but others have a rivalry with Bill and want to be as far away as possible. Visualizing that becomes tricky. If we have 60 Kitty to place, that would be a 60-dimensional space. That is, if Kitty's positions are 1-dimensional, with 3 dimensions, our overall dimensionality blows up to 180. And it's not just a problem of visualization. Our possibility space grows exponentially as we add more dimensions. But the regions of good solutions shrink as we add more constraints, such as making each Kitty happy with its placements. It's much easier to do that for 2 Kitty rather than 60. In numerical analysis and machine learning, this problem is called the curse of dimensionality. As our possibility space becomes sparse, meaning it's big and filled mostly with bad solutions, finding good ones becomes non-trivial, especially if we'd like to do that in interactive times. And generally, the more dimensions you have, the more dark and full of terrors your search space is. So what do we do? Let's consider an imaginary, many-dimensional possibility space. For the purpose of making an example, I'm going to portray it in 2 dimensions. But you can imagine that moving from one point of the space to another involves tweaking dozens of parameters. So just as before, every point is associated with some kind of score. And sure, right now we see exactly where great scores are, but suppose the space is just so big that we cannot physically visit every single point, like I did to make this visualization. We need to deploy some kind of search strategy. And one way of doing it is searching at random. We just traverse the space by randomly choosing direction every single step. But it is a very unreliable search strategy, since we are never guaranteed that anything reasonable will come out of it in a given budget of, say, 500 steps. We can be lucky and stumble upon something great, but chances of that happening consistently are very small. So we can perhaps guide this randomness by asking it to only accept a step in a new direction if the score would become better. This search strategy is called greedy, and it sounds good on paper since it does consistently find okay solutions. However, it tends to get stuck in local maxima, meaning it finds an okay solution surrounded by bad solutions. So no matter what new direction it will try, it will always be worse, so it will just never set out to explore again. And then we have Markov chain Monte Carlo, short MCMC, which I like to think about as something in between greedy and random. Since MCMC, just like greedy, always accepts a new step if it's better. However, if the step is worse, unlike greedy which just discards it, MCMC has a chance of accepting it, a chance inversely proportional to how much worse this new score is. Thus, MCMC will gravitate towards good scores, but not get stuck in local maxima. And with enough number of steps, we can be sure it will find a good solution. But doesn't it all sound like a lot of work? Wouldn't it will take forever to find the best solution in a real scenario? Well, the reality is that we are not interested in the best solution. We are interested in a good enough solution that we can find in reasonable time. And when this time becomes real time, that's when it starts feeling magical. In fact, we would prefer finding a variety of good answers opposed to a single best answer, because this way we can present the user with a variety of alternatives, example of which we will see later. Okay, so we know we're going to be comparing a lot of different placement configurations with one another. You can say one of the core questions of our search strategy is, which one is better and by how much? Because if it's better, we accept it, and if it's worse, we need to know by how much, so we can use this ratio as a probability of accepting or rejecting it. And with Kitty, comparing one Kitty placement to another was pretty simple, because a score was defined by a function that was given to us. All we had to do is plug in the distance between Bob and Mary and see what value our function spits out, and then just use it for comparisons. For example, here, we can easily say that the placement on the right is 10 times better than the placement on the left. But what do we do if we're not given a score function, but just an example of how we want our placements to look like? Suddenly the question which one is better, A or B in this case, becomes rather ambiguous. We can probably pick which one is better based on some kind of internal judgment, but how do we say by how much it's better? We need a numerical way of expressing how similar one spatial object arrangement is to another. So it has to be some kind of function that takes our example and compares it to another object arrangement. We don't know what it is yet, but let's just have a closer look at A and B. Maybe we can find a pattern. For example, we can notice that A is practically the same as our example, except for the rock and the tree being swapped places. So if we just move them around, then A would be identical to the example. And we can probably mutate B to be identical to example as well. And indeed, with just a few more steps, we can. But hey, that sounds like a procedure we can use to judge similarity. If we count how many steps we performed to make A and B look like the example, we can see that A took us fewer steps than B. So we are starting to get numbers that reflect our intuition about similarity. And if we invert the numbers of steps, we get something that is very close to what we think of as similarity. And now we can use these numbers to compute the arrangement A is twice as good as arrangement B. And this was one of our key observations when working on example-based placement, that similarity of two arrangements X and Y can be expressed in terms of minimum number of steps it takes to morph X into Y. And it's important that it's a minimum number of steps, because we can have many possible ways of how to morph X into Y, and if we choose a different one every time, well, that would make our similarity metric quite unreliable. And so happens that we are in a great luck, because this formulation sounds a lot like a mathematical field called optimal transport. So here's a small sketch to introduce you to what optimal transport is about. Imagine two mathematicians lying on a beach. It's lovely sunset, smooth silky sand. And then one of them says, "Hey, why don't we build a sandcastle from the sand on this beach?" And of course, being a practical mathematician the other one is, the first thing they say is, "But how much work would it take to move the sand from its original shape into the shape of a castle?" And the other mathematician would reply, "Trivial, my friend. The work we would need to do is proportional to the total distance traveled by each grain of sand we move. We can minimize this work with this transport plan." And the transport plan just tells us how much stuff we need to move from one location to another, how much sand we need to move from the left hill of the beach to make the castle tower. And usually we are interested in finding the optimal plan that would minimize the work one would need to do. So the other mathematician would exclaim, "The WASSERSTEIN distance between this beach and a sandcastle is not as big as I thought." Translated to human English, that would mean it's not as much work as I thought it would be. WASSERSTEIN distance, even though it sounds very fancy, it's just a minimum amount of work one would need to, in this case, move the sand into the shape of a castle. And the exciting part is that we do not need to find the optimal transport plan to calculate the WASSERSTEIN distance if we are in one dimension. Since 1D WASSERSTEIN has a very neat closed-form solution, which is very fast and easy to calculate. All we need to do is take cumulative distribution function, or CDF, of the castle and the beach, which is a function whose value at a particular x is a sum of all the preceding x's values. So it's literally showing an accumulation of our function values. And to compute WASSERSTEIN, we just need to find an area between the CDFs of the castle and the beach, which in discrete case, such as a histogram, becomes simply a binwise absolute difference. Unfortunately, this trick doesn't work for more dimensions, but soon you will see just how much we can do with that single dimension. So returning to the original question we had of which object arrangement is better and by how much, we can now use our new similarity metric that is defined in terms of WASSERSTEIN distance. So the bigger the WASSERSTEIN distance is, meaning it takes more work for us to morph something to look like the example, the lower our similarity and score are. And this allows us to numerically compare different object arrangements based on the user's example. So far, we have been comparing the whole example arrangement. Unfortunately, with such a formulation, we would only have a good score if we make a perfect copy. If we just deviate a little from the example, our similarity function would become instantly lower. Scared to think what would happen if we have different number of objects? Like, what do we do then? This highlights a fundamental issue. We do not want to generate something that is exactly like the example. Instead, we would like to infer the rules of the example's placements. To do so, we assume that user's placement is a product of object neighborhood rules interacting with each other. And that interaction is the core that makes one's example look like itself. And if we capture those, we can synthesize different but similar looking arrangements. And we do it by asking each synthesized object, "What is your neighborhood?" Then we search for the most similar neighborhood that exists in the example. And it might so happen there is no perfect match, but that would not be a problem because we can just use the same WASSERSTEIN-based similarity metric we've been using before, which would return us a score describing how similar is the synthesized object neighborhood to this neighborhood from the example. And we can repeat this process for every object, and then take a product of all individual object scores to calculate the final score for the synthesized arrangement. I like to think of it as if every object has a preference, like the house wants to be close to the grass but far away from the tree, but the grass wants to be close to the tree, and so on. And then the final score represents how happy is each object with its neighborhood. So by moving the object around, we change how happy the object and affected neighbors are with their new neighborhoods. And we use MCMC to guide this iterative process and find such a configuration of placements that would satisfy everyone. For example, here the example is to have a rock and a tree close together and grass scattered around. And of course, if we change the example, like saying, no, now we want two trees close to each other and rock close to the grass, but the grass can also be just separate from both the rock and the tree, our solutions change as well. And we can restart the possibility space search to find novel solutions, thus we can generate a whole variety of placements that satisfy the example. There is, however, a catch. All of our neighborhoods are 2D, but remember our sketch about WASSERSTEIN distance? Only 1D WASSERSTEIN has a neat closed-form solution. The trick we used for calculating it just wouldn't work for 2D. We started with an approach used in prior work to compress our 2D neighborhood into a 1D representation by considering only the distances to our neighbors instead of their relative 2D positions. And often the distance information is enough to represent the example, and having a WASSERSTEIN-based similarity metric was helping a ton as well. However, in some cases, it was just still problematic. Like in this example, where we want to build a road with the Kittus. And Kittus just completely fails to continue our example and does something that just doesn't correspond to our intuition. So why is this happening? When we compress our neighborhood into purely distances, we lose angle information. Kittus can no longer see the difference between a rock on the left versus a rock on the right. Often, two very different neighborhoods would look exactly the same in Kittus's eyes. Like in this example, the left neighborhood has a clear directionality to it, whereas the right one doesn't. But because the distances of rocks to the center of the neighborhood are the same, those neighborhoods are perceived as equivalent. And the question of how to combat this stumbled me during our first prototype, and was just like sitting at the back of my mind for a couple of months. Until, by coincidence at the same time, both my colleague Tomasz Stachowiak and smart people on the Twitter suggested sliced WASSERSTEIN. So what is sliced WASSERSTEIN? Imagine this is a neighborhood we are trying to compare to some other neighborhood. We literally slice through this neighborhood, in this case with 3 lines, S1, S2, and S3, and we project the whole neighborhood onto each of those slices, thus approximating the 2D positions of our neighborhood with multiple 1D projections. And to compare with another neighborhood, we compare each slice with a corresponding slice from another neighborhood. And then we can calculate the nice and easy 1D WASSERSTEIN for each of those pair of slices. And by summing these WASSERSTEINs, we have computed sliced WASSERSTEIN, which is approximately proportional to the true WASSERSTEIN, but that kind of approximation is completely okay for us because we are only interested in relative comparisons anyway, not the true values. And probably the best part about sliced WASSERSTEIN is that it's still fast to compute. In fact, we can control exactly the speed by changing the number of slices, thus trading off approximation accuracy. And now, Kittus can build roads with us. And note how, by placing the rock kind of to the curvature to the right, the Kittus is also continuing the road to the right. And when I place grass on the right side of the road, Kittus does the same. And if I place it on the left side, Kittus also places it on the left. And the same would happen with trees. Thus, we ended up co-creating a small scene together. Good Kittus. So, to summarize. We've talked about our experimental project Kittiwake, where we set out to explore a feeling of co-creation with an example-based placement algorithm. Then we dive deep into possibility space, which represents all possible outputs of our algorithm. And when the space becomes too big, we need to deploy search strategy, such as Markov chain Monte Carlo. However, for MCMC to work, we need a way to score every new proposed arrangement. Thus, we've covered a way to numerically express similarity between two spatial arrangements of objects, and it's important to note that this metric is not always equivalent to how humans perceive patterns, but it is a convenient assumption. Next, we talked about how optimal transport can help us to formulate our similarity metric and quickly compute it in one dimension. Then we talked about breaking down the example into neighborhood interactions to prevent the algorithm from creating an exact copy of the example and instead synthesize different but similar looking arrangements. Then we showed how to compare 2D neighborhoods when you only have 1D WASSERSTEIN, either by only considering distances to objects or using sliced WASSERSTEIN. And finally, we've shown how it all comes together into Kitty assisting you with placements and co-creating a small scene together. Our example-based placement is still work in progress. There are a ton of things we'd like to try out, such as negative examples, remixing and sharing examples, creating bigger scenes, and also exploring different interaction models. And before we wrap up, I'd like to take a moment to admire the network of interconnected research and ideas that allowed us to build the example-based placement algorithm. That, for example, the very first example-based arrangement paper was inspired by texture synthesis and procedural content generation, and later the idea was expanded with the knowledge from statistical analysis. And even our main contribution, the similarity metric for object arrangements, is again bridging ideas from another field, such as optimal transport. I would also like to take a moment to give a shout out to Tomasz Stachowiak, whose ideas, help, and feedback were a big part of making the algorithm. And I would also like to thank all the people who brought Kittiwake to life, as well as Embark for its amazing brew of so many talented people, super passionate culture, and many fun and hard problems to tackle with an overarching goal I strongly believe in. Here's a list of references of all the papers if you're interested to dig deeper. And I also included the inspirations I used for making the art in this presentation. And one last thing. When it comes to content creation, we as a games industry are very familiar with making content manually. We're getting better at designing rules to automate making content, also known as proceduralism. And the next step, in my opinion, is to go further and ask how we can go directly from creative intent to content by interpreting that intent and extracting the relevant rules that would create the content. And hopefully by doing so, we can also allow more people to experience the joy of game creation together with us. And that will be it. Thank you so much for listening. And if this area of co-creation, enabling others to create, is something that resonates with you, either from technical perspective or UX and design perspective, give us a shout. We'd love to hear from you. Thank you.